Welcome to episode 5 of our series, Quantum Mechanics, the Strange Rules of Reality. We explore the deep science where the predictable rules of everyday life dissolve, and a much stranger reality takes over. This program is brought to you by the Series of Thoughts team as part of the Science Foundation series.
At the dawn of the 20th century, physicists peered inside the atom and found a universe that obeyed no rules they had ever known. This is the story of how they made sense of the impossible. The quantum realm defies our senses. At its core, the unsettling truth is that the act of observation doesn't just record reality, it fundamentally shapes it. Particles exist only as possibilities until you look at them. One of the pioneers of this new age was Niels Bohr. He was a Danish physicist, Nobel laureate, and the architect of the Copenhagen interpretation, the dominant framework for quantum theory. Classical physics is predictable and deterministic. In contrast, quantum mechanics is probabilistic, uncertain, and strange. Particles exist in multiple states at once, and intuition fails completely. Chapter 1. Unraveling the Atom's Secrets. The atom, once thought to be indivisible, was revealed to have a complex inner world. Early models struggled to explain atomic stability and the specific colors of light-heated elements emitted. Rutherford's nuclear model revealed a dense, positively charged nucleus with electrons orbiting it like planets around a sun. However, classical physics predicted these electrons would spiral inward, causing every atom to collapse immediately. Bohr proposed a radical solution: quantized orbits. Electrons exist only in specific, fixed energy levels. In these stable orbits, electrons do not radiate energy. They leap between orbits by absorbing or emitting precise energy packets, or quanta. The Bohr atom suggests electrons occupy distinct shells at fixed distances from the nucleus, not just anywhere. Each shell corresponds to a specific energy level, an idea that profoundly transformed our understanding of matter. Bohr's model was a triumph of prediction. It calculated the exact wavelengths of light emitted by hydrogen, matching experimental data with precision. But a deeper question remained: why were only these orbits allowed? Chapter 2. The Dawn of Probability. The deterministic view of classical physics begins to unwind. Quantum mechanics replaces certainty with probability, trading exact trajectories for clouds of possibility. Wave-particle duality describes the double-edged nature of reality. Light acts as a wave, creating diffraction, but also arrives in discrete packets called photons. Electrons, particles of matter, also behave as waves, having a wavelength. The wave function, or psi, is a mathematical function that describes the complete quantum state of a particle. It tells us the probability of finding a particle in a given location, not its exact position. The particle exists in a superposition of all possibilities until measured. Around a hydrogen atom's nucleus, the electron doesn't follow a fixed orbit. Instead, it occupies a probability cloud. Position is not a fixed fact, but a distribution of chances. Max Born's breakthrough, the Born rule, established that the square of the wave function's amplitude gives the probability of observing a particle. This marked a shift from determinism, establishing that the universe deals in probabilities and chance. Chapter 3 introduces the Heisenberg uncertainty principle, formulated in 1927. This famous but misunderstood idea is not about faulty tools. It is a fundamental law baked into nature itself. The principle describes an unbreakable trade-off. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is described by the equation shown. Imagine trying to photograph a moving car. A sharp photo freezes its location but tells you nothing about its speed. A blurry, long exposure captures its motion but blurs its exact position. You can't know both precisely. The uncertainty principle has profound implications, marking the end of determinism. We cannot have perfect initial conditions, the future is uncertain and probabilistic, and reality is fundamentally fuzzy at the smallest scales. Chapter 4 covers Bohr's complementarity principle. He argued that certain quantum properties are complementary. They are equally real, but they can never be measured or observed at the same time. Wave and particle behavior are two sides of the same coin. An experiment set up to detect wave behavior shows a wave. An experiment set up to detect a particle shows a particle. But you can never observe both simultaneously. Bohr stated that measuring one quantity of a complementary pair excludes the possibility of measuring the other. The act of measurement is not passive. The choice of what to measure actively determines what reality reveals. The double-slit experiment demonstrates this vividly. Electrons create an interference pattern when unobserved. But when detectors watch which slit they go through, the pattern vanishes, and they act like particles. The experiment dictates the behavior. Chapter 5 explores quantum paradoxes and puzzles. The logical consequences of quantum mechanics lead to bizarre thought experiments that reveal unresolved tensions at the heart of physics. Schrödinger's cat illustrates how superposition extends to the macroscopic world. The cat is sealed in a box, and quantum logic dictates that until the box is opened, the cat is simultaneously alive and dead. The question remains, when does the superposition collapse? The cat thought experiment is the most famous example of the measurement problem. Quantum superposition appears to require impossible simultaneous states for macroscopic objects until an observer forces reality to choose. The EPR paradox, proposed by Einstein, Podolsky, and Rosen, argued that quantum mechanics must be incomplete, demanding hidden variables to explain correlations between distant particles. Bohr countered that the theory is complete within its own scope, a view later validated by experiment. Entanglement is the phenomenon Einstein called spooky action at a distance. The states of two particles become instantly correlated, regardless of the distance between them. Measuring one particle instantly determines the state of the other. Chapter 6 addresses the quantum legacy. Quantum mechanics is the foundation for modern technology, enabling everything from lasers and transistors to MRI scanners and the revolutionary field of quantum computing. Quantum mechanics works with unmatched precision, yet its philosophical meaning remains intensely debated. As Bohr said, anyone not shocked by quantum theory has not understood it. Join us for the next video, where we explore the evolution of life.